Now this is from that video visualizing the nucleus, and I would like to know, is that actually truly a picture of a neutron versus a proton? I find it hard to believe, but I do see something that's quite intriguing. This has a membrane around it. All right, you see all the little particles inside there? Do they actually see this? This is what I have a hard time believing, because they say these are the quarks, and the same quark structure here. However, you see this has a membrane around it, and this has no membrane. A proton is a charged particle, so it either wants to take on another electron or it wants to give an electron up. This is like sealed. It's like border. It's got a border around it. Stay out and I'll stay in. I am neutral. I don't want to add to you and I don't want to take anything from you. This says I'll take one from you or I'll give one to you. And then we'll both be stable. This one says I'm stable by myself. I'm good to go. Is that real? I don't know. That's what they're saying. Charged protons, neutrally charged neutrons. Okay, my outstanding friends, sometimes things just go your way and sometimes they don't. Well, guess what? They're going my way today. MIT is going to be talking about visualizing the nucleus of an atom, which I have been showing in my dipole electron flood theory for years now. Also, MIT just announced that the oceans did boil, just as I have been claiming for years now. Everything's going my way. Now, I'm going to have to pick and choose going through here because I don't think they'll let me play clips from this because it's got a music thing in here. When they have music, they don't let you play. No comments, nothing going on about this. I would love to comment on it, and I will. But let's see what they have to say. I haven't watched it yet. I'm going to find the clips that make sense, and we'll take a look at them. So this is visualizing what the nucleus looks like. 400 BC, they were talking about atoms, a building block that could not be broken up. That's what they always thought the nucleus was. Of an atom, each atom, they had a nucleus that couldn't be broken up. Well, now they realize that's not the case. Okay, they're getting down to the tiniest little bits and pieces, 1 nanometer. And you see the 2 little Mickey Mouse ears on the big ball? That's water. 2 hydrogens and an oxygen. And so they're homing down in on this. Wait a minute, let me see if they... Anyway. Let's go a little further, but you have to be able to see down really small if you're just looking. When you're looking at energetic reactions, you don't have to see down in this range. You're looking at the energy coming off, and that's what we're going to be looking at. Okay, so here's what MIT says the proton is. We arrive at the nucleus of a hydrogen atom, which is a proton. Now let's see what they say it's made of. Okay, here's where we might have a little confusion. It says inside the proton, things are moving incredible speeds. It's just flailing away in there is what they're claiming. All right, incredible speeds, but infinitesimally small volumes. So tiny, but they think inside of here it's just buzzing away like crazy. All right, and they say we're deep in the quantum realm. Well, I say a proton is not that. I say a proton is this. And it's made of dark matter in the center, surrounded by the white particles around it, and I actually can show that. All right, anyway, so they're inside the proton. They say we're deep into the quantum realm. And this I'm not sure I can go along with. They say that the proton has a radius of 1 femtometer, which is 100,000 times smaller than the size of a hydrogen atom. So they say the proton is 100,000 times smaller than the size of the hydrogen atom. Well, where's all that rest of the... Because a proton is supposed to be the building block of hydrogen. All right, see, this is where it gets spooky. It says the proton exists in a quantum state that changes based on how you observe it. a proton is just a bunch of little dipoles. Let me show you what the real proton is in my model, and then we'll go on with this, because I can actually show you what I believe is the proton based on our experiments with light. Okay, my model is based on everything being a dipole. You see the black and the white together and the black and white together? They're two like bar magnets that stick together, and that's a photon. And we could separate the black from the white. Fermilab found the same particles, only they see them in a splash of material. We see them coming, they're light. And we could accelerate the light, which is not supposed to be allowed. Einstein was wrong about basically everything he said. We are able to break apart the black from the white and separate that and create sterile muons and electron showers. That's the holy grail. This isn't my doodle, that's from Fermilab, or CERN, one or the other. And Fermilab found these particles, and here's the article from Fermilab. Well, first of all, this is my article. I say this is what a proton looks like. Anatomy of the proton, there it is. And there's a dark core, because there's black and white particles. They never knew this before, and they still don't know it, because they refuse to look. And these are the only two particles that exist. And this, it can have green or blue or red or whatever color, but the black is always the same, and it's always the same size, and has all the weight. It has no weight and all the energy, and it comes in all the different colors. Gluons are the smallest stable particle there are, which are nothing but electrons, but they're bar magnets. We always thought just there was a negative, but we never knew the positive was hooked to the negative, which it is, as I just showed you. And two of them back to back make a photon. Photons have weight. They're not massless. They say, oh, they're massless. No, they're not, absolutely not massless. And chemistry's got to change. Space, redshift, throw that out the window. There's no such thing as a redshift. You know, light will shift red, but it's because it's slowing down, not because it's being stretched, pulled away. Because of expansion of the galaxy, that is just total nonsense. So this is what a proton looks like. Now let's go back to MIT and see what they have to say. Now here's what, originally they had just a proton was that couldn't be broken. Then they said, oh, there's got to be some quarks and this and gluon, you know, leptons and hadrons. They got all kind of exotic names, and they call it a particle zoo. Well, it's not. They're made of these, and each one of these is a dipole. It's a magnet. That's all it is. And at 1839, I believe, is the number that they become stable at, if Millikan's oil drop is right. Because he said that every electron weighs 0.0005,854, something like that. 0.00058 atomic mass units. And if you take and divide 1 by that number, you end up with about 1839, 1840. So I say that is a proton, not this. Now they say the proton exists in a quantum state, changes based on how you observe it. No, it doesn't. A proton is a proton. Now, one other thing can happen now. You can lose a couple of these electrons, and it'll still be a proton, but it won't be a complete one. It'll be what they call an isotope. It'll be a charged particle. It will either want more particles to come in, or it will want to attach to something that will accept it and become stable, because this is not stable and the other one was not stable. Between the two of them, they make stability. That's what isotopes are all about. However, it's still, you would call it a proton. And the same thing with atoms. Atoms are all different sizes. If you take this carbon atom, you can have all kinds of different carbon, all different sizes, and all it means is either there's not enough of these or there's too many. And at a certain exact number, it will be perfectly stable. When it gets below that number, it will want to take some more on, and they call that half-lives. It gets above that number, it's unstable, and it will want to shed some off. And again, it will decay. They call it isotopic decay. I get a little chemistry here, a little physics. See, they're going high shutter speed. They see an ocean of gluons. Like I said, each one of these is a gluon. Now, don't forget, they're just observing this thing, you know, taking shots at it and seeing what's going on with it while it's sitting there. We're seeing them as it's coming through the Venturi. We're seeing the light actually manifesting itself. And the light is way down smaller than this. This is 1,840 or so, 1,839 of these little particles. When we're using our stuff, we're down here. You actually have 2 of them. Just like that. Instead of this. So when they smash their particles and you look at the debris that comes out, they just have a bunch of debris. When we look at our particles, we can see them coming on down the road, and then we can see them divide. Much more elegant using light than using protons to look inside to see what is inside of a proton. Because light is part of the proton. It's much smaller than a proton. So they see an ocean of gluons, which each one of those is a gluon. See, this is where they lose it. They say at different speeds and shutter speeds, we see quarks and anti-quarks and pairs of this and hadrons and all kinds of things. It doesn't matter. It's all made of dipole electrons. See, then they go into proton, neutron. They say that not only positively charged protons, but neutrally charged neutrons. All it is this is an uneven number, which means it's charged. It wants one more to become even. And this is an even number, which means it doesn't want to give one up or take one on. When they're uneven, it says, I need one more to become complete. All right, and that's how they bond. All right. When they're even numbers, they call them neutrons, and they just throw them in here and there. They're not. They don't understand neutrons. Neutrons is just one more particle than a proton. I have no idea how they came up with this. Neutrons on their own are unstable and will quickly decay. That doesn't make any sense to me, but who knows? Okay, this finishes it off. We're only 3 minutes in, and they realize they can't see down inside to see what's going on. It says neutrons remain stable when bound to a proton by the strong force in the nuclei. That's just not correct at all. They're not bound to them by some strong force. Well, okay, I guess we can wrap it up just about right here, because they're not going to look into the nucleus. I thought they were going to look into the nucleus. They're looking into the nucleus of big molecules. I look into the nucleus of a hydrogen atom, and I say that is the nucleus is made of dipoles. Now they claim that neutrons remain stable when bound to a proton by the strong force in nuclei. Or I say the neutron is just one more electron than a proton. All right, here's what they're saying right now. They're only going to look at protons and neutrons in mass. They're not going to get into the particles like I'm talking about, but I will, and I'll show you. They're talking about oxygen-16, has 8 protons and 8 neutrons. It makes 16. See, they say if you really look deep to the fundamental quarks and gluons, the constituents of the neutrons and protons would appear, but they're not going to do that because they can't do that. You see, it's just for our purposes, they are hidden. In other words, they're just looking at this. Now, they're saying this is a stable oxygen-16 molecule. That means there's 16 big balls like this, or 16 big balls like this. And 8 of them are protons and 8 of them are neutrons. And they're floating around in a nucleus. That to them is a nucleus. To me, hydrogen is with the nucleus that I work with. I work with the proton and the neutrons. They're the same, except one has one less than the other one. The one less is the proton. It's unstable because it wants to have one more, or it wanted to give one up to somebody else to get down to an even number. They're looking at this. Let me show you what oxygen-16 really is made of. You won't believe it. You will not believe isotopes, my friends. Now, I told you that this is what I am going to say is a proton. Now, every single atom there is has all kinds of what they call isotopes. how could they have isotopes, which means they're not the same size? And here's what I covered this up so you wouldn't get scared. This is isotopes of oxygen. Well, what does that mean, isotopes of oxygen? Oxygen is supposed to be just oxygen, right? No, it's not. There's all kinds of oxygens. There's only 3 known stable ones, which is oxygen 16, 17, and 18. What does that mean, 16, 17, and 18? Here's the deal with atoms. Here's what atoms are. Each one of these is an atom. Here we got oxygen. All right, it's got 16 is its weight. They say there's 8 protons and then 8 neutrons. We'll talk about that. And that's oxygen. So you think, oh boy, that's it. Here's the atomic weight and here's the number of protons. Everything is good. No, it's not. This is oxygen. Look at this. Here's the oxygen. And then they say, we got oxygen here, and it has 8 protons, but it only has 3 neutrons. Therefore, its weight is here, 11.05. And it's only stable for a certain amount of time, a half-life. It's not stable. And it'll stay that way and then it'll click over and change. And the change is the decay mode, and it changes into carbon. All right, so oxygen comes back down to carbon. All right, it lost a whole bunch of stuff, or gained a bunch of stuff. Whatever happened, happened. Then you go to oxygen 12, 13, 14, 15, and here's the 16, 17, and 18, which they say are stable. These all have half-lives. They're going to break and fall apart and so forth. Now you go over the top of that weight, and you're up into the 17, 18, 19, 20, 21. It's only supposed to be 16. See, these are in the 16 range, 15 and 16, 16, 15, 16, 17, right in that, and they're okay. But now you go 17, 18, 20, 21, 20, way up, now, you know, they're heavy, and they're going to fall apart. So oxygen is not just one big ball, and it's solid. No, it's all of these little pieces can fall apart one at a time, and they will decay. And at that time, the decay going upward. You see this? We were at oxygen, and this is the decay mode. Here's what people don't understand. You can go decay up or down. So we decayed from oxygen all the way down to carbon. Then when we get closer to neutral, when it decays, it comes down to nitrogen. You see the N, nitrogen? It can even come way down to helium. Break into heliums, that's what they say. Once you go above stable of the oxygen, when it decays into fluoride. Fluorine, I'm sorry. All right, so you can go up or down from the decay. That's what they don't understand. So this is, they cannot explain isotopes with the standard model. Nobody even tries. They just don't even talk about it. Can't be done. The standard model won't allow for these changes in weights and so forth. It can't happen with the standard model. So, like I say, we have to change the model, and here it is right here. It's a dipole electron flood theory. Everything is made of these little particles. And the black gets pushed all the way to the center, and the white particles surround it. The blue is real tight, and to pull that away is really hard. That's why blue is a very, very energetic particle. Green is a little less energetic, and red is low on the energy low. Okay, they had no comments up here. I can't believe that's what's going on, but they had no comments, so I left one up. I said, come to my channel, see muons, electron showers, photons. We use laser light and tuned venturis. Now this is MIT Department of Physics, and here's what they say. And I've contacted virtually everybody about my research, and they're saying that for the first time, the size, shapes, and structures of the nuclei in the quantum realm are visualized using animations. I'm not using animations. I'm using the actual pictures of the light. and the light acceleration, the muons, the electron showers, all of that. They're explaining their animations. And work was made possible by funding from Jefferson Lab. I've been trying to get through the Jefferson Lab for a very long time, and I can see they're all trying to do close to what I'm doing, but they're trying to make it so that it's so expensive that they can justify all their heavy equipment funding, where you don't need that. You just need lasers and a little Venturi, a few $100s. We did everything that I showed. So here's the real situation, is that we found these particles. These are Fermilabs. This is right from Fermilab, their article, over 10 years ago. We found these over 10 years ago. I reported it to Fermilab. I reported it to CERN. I reported it to Jefferson, JPL, NASA, all of them. And I said, we found the photons that you guys are looking for. These are the particles that Don Lincoln at Fermilab found. And we found them too. But we accelerated light using Venturis, the two round pins here and here, which force the light to come together and spray the white away and keep the black from coming through. And I saw that, I forget who, I guess it was CERN, the Large Hadron Collider. They're doing the same thing right now with these little, they're still trying to justify their big expense things, but they're using, I forget what they call them, mini accelerators or something. They're just little tiny things where they're whacking into it and then picking up the hit on the other side, but they don't need to do this. They're not doing it in the most cost-effective way, let's put it that way. We just use laser light. Laser, boop, boop, boop. And it saw the Venturi here, and it has to speed up to go through the Venturi. There's nothing else it can do. All of this light here, these are nothing more than beams of light too. You would never see them except they're being crushed backwards and lighting up. This one's going forward and starting to glow, but not like these. These are being pushed back at. And this, my friends, I'm sorry to say it's true, is fission, and that is fusion. And this right here is what you want to put in the batteries. Yep. Okay, so these are the particles that we found from light. And these are photons. Photons stimulate CMOS. And I went to the University of Geneva for particle physics. And I told them we could see this stuff, and they originally were saying, no, it's impossible, blah, blah, blah. Well, by the time we were done, they did agree, wow, that's amazing. And they did upgrade CERN to use CMOS for detection. Just look it up. Say, did CERN upgrade to use CMOS for detection? And they say, yes, they did. Because CMOS is not, you don't have any observer effect. You're not pushing light or anything in to look. And you're not, having something in there to absorb any of the energy. You're just waiting for the energy to hit you back here with the CMOS. There's nothing better. That's why we had such fabulous results. Now, they could see those particles. This is, where is it? Right here. That's the article from Fermilab. It's 2013. And again, I got a hold of Don Lincoln because he asks at the end here. Every time he says, here, Don Lincoln, want a phrase defined, have a question? I said, yeah, we found your particles. And he was abusive. And it wasn't good. It was a very bad discussion we had. And he's blocked me from everything. And he's spending our money like water. And this is the reason why I said you can use CMOS, it won't interrupt, it won't hurt your readings. Here's what he's saying. If you magnify extended particle, look bigger. A point-like particle will not change in size, but the more closely you look, the stronger the field becomes. No, the more close you look is the more light you flood into it. And it responds back by saying, don't push your field into me, and it gets more strong, the field. The field goes, don't push me, I'll push you back. I call it push to shove. And it does exactly what he said they do. The fixed particles are fixed size, never changes, it's a solid, it has all the mass, and the other one has a fuzzy edge around it and has no weight whatsoever. And that's exactly what we found, as I have shown you right here. These are the particles. Here they are. The black one is the black one. This one here is whatever color, because we have them in green and blue and red because of the color of the lasers. And we did accelerate that light, which you're not supposed to be able to do. Light is light. I don't care if it comes from a laser or a candle. It's supposed to go the same speed, and it does not. And we can accelerate it, we can slow it down, we can split it, we can fuse it back together. And this is the distance of entanglement. They're trying to figure out entanglement. I think it was MIT. They're looking at entanglement, how long they stay disentangled when they get separated. And we can actually measure the distance. This, like I say, this is not big, expensive stuff done here. Very simple, very easy. And if we could take that white and use it to charge batteries and so forth, boy, there would be nothing better than that you could possibly imagine. Because all you're doing is taking a laser and shining it into a Venturi and picking up the white on the other side. And that would be hundreds of times more energy than you started with. That's what they say. Electron showers create scads of energy. And that's what goes into a battery, is this white stuff, because it has no weight. And it fills the battery up, and then you can drive all day long, and then you still have the same weight in your battery, because all you're using is this white. It's coming back around in the battery. So this is what we need to do, is to get that white, and here it is right here. All right, if you're interested, just keep your eye on my channel, because I'm just going to keep going over and over this until they start to look at this for what it can be done. They're showing simulations of this and that. I showed the actual experiments, and this is what I'm saying most likely the atom looks like. Now, I looked at this too, which would be a different configuration where you had a black and then a tightly held, and then another layer of black and then tightly held green, but I don't think so. I think the black completely congeals to the center in this model. There's two possible models. This is my favorite. But this is the two particles. They make up everything there is. That's it. That's it. That's all that exists. All right. Now, this is going to be the differences from the standard model. Not much. Not a whole lot. And this was done on Rod Warren's light experiments, are the things I've been showing. Now, he has disassociated from this now, but I hope he gets his credit for what he did, because when I saw the experiments he was doing, he didn't realize what he was doing. He was trying to get the double slit experiment, but he was using a Venturi, and I said, how did you do, because I saw the results, I said, how did you do that? And he explained to me that he used literally nails, round nails, and he had 3 nails, so he had a double slit, and he shined light through it when it came out the other side, and he used a Samsung phone, and I have all the stuff right here. I get the same stuff, and I just was not, I didn't have the time to do it, and I was not good at doing it, but I know it's been done because he did it. I got more pictures than you can imagine of the light research. I have hundreds and hundreds of pictures of these photons splitting, dividing, red, green, blue, how the light comes in. I have so much, it's just unbelievable. But this, to me, is no question, this is what they're talking about at Fermilab and CERN and everywhere else, and they're the smallest particles that exist because they are light, which is supposedly an elementary particle. They say they have no mass. They absolutely 100% have mass. And they work on a really interesting principle of magnetism and mass, which causes you gravity, dark matter, magnetism, mass, heat, energy, all of that is locked in that little bugger right there.